Hi, thank you all for coming, and thank you, Brian, for the very kind invite. It's great to be here. So my aim is to give you a very broad overview of quantum computers, and especially focusing on trapped ion quantum computing, and explain some of the quantum weirdness that makes these machines tick the way they do, and maybe also hint at some of the applications that we already know about, and give you some ideas where this technology is going. To start off with, so I'm a senior scientist in the Ion Quantum Technology Group at the University of Sussex. It's a reasonably large team, and I don't really get to do any of the fun work anymore, so it's really these guys on the right, the postdocs, PhD students, who are doing most of the exciting work, and then I get to come up here and show you guys. So fantastic team, really good people, and ever growing. I should also point out that we don't just work on quantum computing, we also work on developing quantum sensors, portable quantum sensors, where we'd like to sense very weak magnetic fields, but I won't talk about that today. The other thing to point out is that since we're in Oxford today, I should point out NQIT. NQIT is one of the 4 quantum hubs that are currently running in the UK, and this particular quantum hub is focused on network quantum technologies, really quantum computing. We're part of that, Oxford's part of that, and various other partners who all work towards the end goal of having a quantum computer. Now, as part of this hub, there are 2 demonstrators to be developed. One is the 2020 engine at Oxford, and then we've got the microwave engine at the University of Sussex, which will be the topic of my talk today. But just so you know, you've actually got quite a lot of quantum computing expertise here as well. The bad news is that we can all go home because we can buy them. We're just wasting our time, pretty much. This is down near Lewis, I think. So yeah, that's it. But to be honest, I mean, joking aside, this is really the dream. I would love to see this actually being a real quantum computer shop in X amount of years. So that's really what we're, in the long, long future, would like to maybe have. So let's move on to some quantum weirdness. Who's heard of quantum physics? Perfect. Can someone shout out some quantum weirdness that you've heard about? Entanglement, yeah, that's one. Einstein didn't like that one. Didn't really believe in it. Anyone else?
Uncertainty, Heisenberg's principle.
Yeah, that comes in as well. Okay. Superposition. Yeah, superposition. That's another important one. Good, you guys are experts. I can pretty much skip this then. So, in the quantum world, everything seems very counterintuitive. It's because we don't really experience that in our classical world. So, for example, a mechanical object can be in 2 places at the same time. It means I can be here and I can be on that side of the stage simultaneously, which is quite cool. You can also have an atom move forwards and backwards at the same time. We do this in the lab routinely. That has definitely been shown. An object can tunnel through a wall. This has all been done. And there's also entanglement, which freaked Einstein out completely. And I'll explain that in a little more detail later on. But the interesting thing is, which some of you might not know, is that quantum effects have already changed our lives. It's not some weird theoretical thing that hasn't really done anything useful for us. We're used to it all the time. Transistors, a classical computer wouldn't work without quantum effects. If you look at how a transistor really works, you couldn't really describe it without some quantum theory. And the same holds for a laser. Wouldn't work without quantum effects. What's really changed in the last maybe 10, 20 years is that we've become increasingly good at harnessing quantum effects and turn them into something really useful. So we can really manipulate them very precisely to turn them into new technologies. One is a quantum computer, and that's what I'll be talking about today. I've already very briefly talked about quantum sensors, and there's also quantum communication and many other technologies that are being developed at the moment. And that's really why quantum technologies as a whole is such a big thing at the moment, because there's a lot of cool things one can do with this quantum weirdness. But you could ask, why should I care about a quantum computer? I've got computers here, they're doing great things, they can basically do everything that I need them to do, and most of you may have heard of Moore's Law, which is basically promising us ever faster computers at a very steady rate. Now, one thing to point out is that Moore's law is expected to not be there forever or not hold forever, which means at some point we'll have to think about new technologies anyway if we want to get faster. But the more interesting point is really that even if Moore's law was to hold and we would go on for 50, 60, 100 years, there are certain problems that we'd like solving that these machines, even in 100 years' time, wouldn't be able to solve. And that's really where quantum computing will come in. It's not just a small improvement or making them twice as fast or having a calculation that runs 10 times as fast. It's a completely different game that we're going to get into here. So quantum computers may be something useful to look into. Like I've mentioned, they're completely different. They use a completely different technology. They don't really operate the same way. But we believe there will be some similarities, especially in the way this technology will be developed. So I'm going to sometimes refer back to what happened in the classical computer game back in the 40s and 50s to kind of give you an idea of what point we're at the moment and where we're hoping to go. So what can a quantum computer do? That's a good question. Like I've said, it can really solve certain problems which you would never submit to even the biggest classical computer on this planet. There are certain problems that these machines just cannot do, and it would take 1,000,000 years to solve. A quantum computer would do this in seconds. Because it's a completely different game we're in here. But how do they do that? How can they get away with that? So one core ingredient that we make use of is quantum superposition. So like I said, something can be in two places at the same time. That then also means that if I have a bit, so in a classical computer, the information is really stored in classical bits, and that can be 0 or 1, and that's great, works very well. In a quantum computer, we have something called quantum bits, or qubits, and they can also be 0 or 1, but because of this superposition principle, they can be 0 and 1 at the same time, and that's really important. The second core ingredient that we have is entanglement, this spooky action at a distance. Freaked Einstein out completely. I can maybe highlight why he really didn't like it. Now, if you, for example, have, if you two throw a coin, you will randomly get heads or tails, right? Completely random. If your two coins were entangled, then every time you get tails, let's say, you will get tails. No matter what. Every time you get heads, you will get heads. And you can be in different rooms, you can be on different planets. That will always happen instantaneously. And this is something that didn't go well with Einstein at all. But he was wrong. This happened. This has been shown in the labs. We do this in the lab continuously. This is what we need to actually operate a quantum computer. And we've been getting very good at really creating these sort of entangled states, these entangled systems in the laboratory. To kind of show why this has such a big effect on computing, if, for example, you have 2 bits, so really the smallest classical computer, then the sort of number that you can represent at any one time would be something like 0, 1. That would be a number you can represent. Or it could be 1, 1 or 1, 0. Now in a quantum computer, if you have 2 bits, all of a sudden you can have these 4 numbers at the same time. Now if you think this through and you go larger, so let's say you have 100 bits, you could have one number, a 100-bit string. In a quantum computer, and I'm not going to try and get that out, you could have this massive number, different numbers. So, billions and billions of different numbers. And that's really where some of the power comes on. It's a completely different scaling. And that's what makes this quite exciting. And very quickly, really, you're going to approach the number of particles in the universe. I think as soon as you hit around 200 qubits, that will be enough to represent the number of particles in the universe. So pretty crazy. So in terms of where we are in understanding what really these machines will be able to solve, what sort of problems, we don't anticipate these to be any better at word processing and these sort of things. You're not going to use it for that. But there have been some really smart people developing some great algorithms that you may have heard in the news. There's, for example, the factorization algorithm, which allows us to make these big statements that, for example, RSA encryption would be able to be broken, because quantum computers are known to love to factor numbers. This is something classical computers hate doing, which is why RSA encoding, a way that a lot of your data is secured at the moment, works on the principle that you have to factor a large number. Since a quantum computer would just do that instantaneously, it's a worry. And there are various other ones, search, there's also machine learning, which is a hot topic at the moment, and I can talk about that a lot afterwards. We know already a lot about where quantum computers will have applications in making machine learning much, much better. So there's a new field, quantum machine learning, coming about at the moment, which would be quite exciting. But the important point to make is, so there are about maybe 100, well maybe 50 quantum algorithms at the moment. The important thing to notice is that we're really at the beginning. This is, a new field. People haven't really thought so much about developing these algorithms. If you imagine how many programmers there are in the world developing algorithms for classical machines, we're nowhere near that in the quantum computing game. So that's definitely one thing to note, but only at the beginning, and continuously uncovering new applications. But to give you an idea of where these applications may be, there's most certainly these 4 fields are hot candidates at the moment. We're working with a lot of industry partners to really find out where exactly these machines will be able to help. In energy, there's most certainly a big area where whenever you deal with big data, trading optimization, or optimizing how you route energy to households, etc. And that really goes through defense, finance, etc. One thing you'll be able to see is that the sort of things I've listed here either involves large amounts of data or a problem where you have to try lots of different possibilities to arrive at a solution. Now, if you remember, superposition means I can have a quantum system in many, many different states, which really means that if I have a problem where I have to try 100 different ways before I get an answer, I can look at these 100 different options simultaneously. Whereas in a classical machine, I would have to go the naive way of, I try that way, no, it didn't work. Try the next way, didn't work, and so on. So it's almost like a massive, big parallel computer. That's how you could think of this. And this is really where some of the early work has been focusing on those sort of problems. And that's where some of these areas come from. The other thing, and that I find extremely exciting as well, is that everything around us, every object, etc., can really be simulated or understood using quantum theory. Which means if you want to understand nature, if you want to understand chemical reactions or anything really, the universe, then it makes a lot of sense to use a machine that uses the law of quantum theory to understand these systems, rather than using a classical machine which tries to brute force understand these systems. So we're most certainly very hopeful that these machines will have some amazing applications in science and just understanding the world that we live in. And that's really on the simulation side, where you'd simulate these quantum systems using a quantum computer. So yeah, I've mentioned this, and I haven't really discovered the most important quantum computer application yet. I definitely don't think so. And it only really takes looking back at what happened with classical computer to understand why I'm slightly optimistic that there's still a lot more to be uncovered. So if you look at what Thomas Watson, for example, said in 1943. He was very convinced that there's probably a market for about 5 computers in the world. A lot more computers in this room at the moment. So he got that slightly wrong. And for many years, people thought, quantum computers, are they really going to work? What are you really going to use them for? It's a similar story. Equally, if you look at how people, describe what people said about ENIAC, for example, the first classical machines out there. The electronics people said there were too many vacuum tubes and it would never run. The mathematics people said there were no problems complex enough that computers were needed. And it's very similar. Right now we still have a lot of people who look at our systems and they're messy. They really are, and they're very complicated, and they break a lot. And it's like, why? This will never really work. And there aren't really any problems to solve anyway, because what we have nowadays will do. So I feel we're at a similar point almost. And here, just to put this into numbers roughly, if you go back to the 40s, there are maybe 5 computers and maybe 50 programmers around, and that's roughly the state that we are right now. There may be 5-ish small quantum computers that can do small, cool things, but not quite the point yet that they can, really do something amazingly useful. And there may be 50 odd people around the world looking into developing these sort of algorithms. So, how do you build a quantum computer? This is what I'm going to focus most of my talk on, and I think Brian mentioned this earlier as well. One of the reasons I'm standing here is that about a year ago, we had quite a significant breakthrough where we unveiled the first blueprint on how to construct a quantum computer, to really show people that this isn't just weird stuff that people do in the lab and will never really be useful and can't really be built on a large scale. We really sat down for a few years, actually, thought this through and came up with a construction plan, so to speak, and how to build this large machine. I'll try and go through that in a short way now. But first you could argue, what sort of technology would you really use for that? What sort of system exhibits these quantum effects that we'd like to make use of? Now, lots of different people use lots of different architectures out there, and it's not really decided yet what the winning architecture will be. However, one thing I can say as of today, these two here, the superconducting circuits and trapped ions, are the two leading platforms. Most of the industry investment, and academic investments have gone into these platforms, and they've shown some really amazing results in the last few years. On the superconducting circuit side, I won't talk about that. It's not something we work with. But just to give you an idea, these are really great systems, getting a lot of attention. But some of the challenges they have to face is that they have to cool these whole systems down to absolute zero Kelvin, basically. They're sitting at minus 273 degrees C. And later on, you'll see how big these machines are. It's a challenge, but most certainly probably doable, but it's something we're a bit scared about. Trapped ions, they also have their challenges. But some of the good sides of them are that they can work at room temperature or very light cooling. They don't need to be cooled down to minus 273. And it's comparably easy to do some very high fidelity operations on them. So these are very good, clean systems to work with, in theory. And that's really demonstrated here. So the first thing to highlight is that trapped ions, which are basically charged atoms, they are identical. You can go to San Francisco or somewhere in Australia right now. If I'm telling you I'm using an ytterbium ion, for example, they will be the same everywhere. So wherever I kind of have these systems, they will be the same. Superconducting qubits, for example, they are fabricated. You go into a clean room, into one of these microfabrication facilities, you make them, and they're all slightly different. And that's a challenge when you scale up, when you want to have lots of these things. So one of the advantages that we most certainly have is that they're just identical. They're also very well isolated. These atoms really, they can store information for a very long time and don't get disturbed too much if we play the game right. And the other thing, what I mentioned before, is that they can be controlled extremely well. Just like in a classical machine, we have to do certain gate operations on them to process the information that's inside them. And these are most certainly world record numbers across the different architectures where trapped ions are leading at the moment in terms of the success rates that they can achieve when implementing these logic gate operations. Also, and I hope I can convince you of that later on in the talk, that we have a reasonably good route to achieving these large-scale devices. However, it is technically demanding. There's a picture of one of our labs at the University of Sussex down there. If you were to come and visit us, and you're more than welcome to do so, it's a mess. It looks like a mess. It's very complicated, but we know what we're doing. But it's not easy. So how do you work with these trapped ions? And rather than me trying to give you a not so good explanation, we just go to Tom Clancy because he gives an amazing explanation. So, too bad this isn't like quantum computing. You confine ions in webs of magnetic and electric fields, hit a trapped particle with a burst of laser light to send it into an excited energy state, then hit it again to ground it. That's your switch. Rows of ions in a quantum logical gate, giving you the smallest, fastest computer on Earth. Neat, clean, perfect. Pretty good explanation, apart from the neat, clean bit. Not quite so, but that's actually a surprisingly accurate description of what we do on a day-to-day basis to operate these machines. But I'll take you through that with a couple of pretty pictures as well. So when we want to trap an ion, so this will then form our quantum bit. Now an ion is a charged atom, which means you can use maybe an electric field to hold these in place. You don't want them to zoom around. You want them to be in one place so you can work with them. Now, unfortunately, you can't use static fields, only static fields to hold them in one place. Physics law kind of tells you shouldn't do that. So we play a trick and use an oscillating electric field, where the hope is that this charged atom will sit on the top here, and every time it tries to roll down somewhere, it'll be kind of held in place using this oscillating field. You may not believe me, you shouldn't believe me, but I've got proof. So we can start with this mechanical description of that. The saddle is now the oscillating potential, and you just saw that when it was not rotating, the ball, which is the charged atom, rolled off, but when it's oscillating, it stays there. I'm going to click next because it does roll off after a while. But we can also go a little smaller. So if we, for example, have some charged particles that we just charged up and throw into this little machine here where we apply a very strong oscillating electric field, then you can see that these charged particles are hovering in free space. So here, no cheating going on here, they stay there for a very long time. So that's working very well. But we have to go smaller. We have to go to individual trapped ions. So the way we do that is we manufacture ourselves some metal-type structures that we can apply these fields to. Now, traditionally, people use these sort of macroscopic style traps where you apply your oscillating fields to these metal structures, and then somewhere in the center here you trap individual ions. Now, when we want to scale up and we want to be a bit more sophisticated, it's useful to go to microfabricated structures where you may think, well, you told me microfabrication is annoying and it's not very good. That's the downside of superconducting qubits. But what we're doing here is we fabricate the trapping structures that you can see here using some fabrication techniques, but our quantum system, our qubits, are in a way levitating above it, away from this noisy, imperfect geometry. So these identical qubits are hovering above an imperfect surface. And that makes this quite powerful. So if we don't get the fabrication exactly right, that's okay. It doesn't affect our quantum system in a way. So these are the sort of structures that we fabricate ourselves actually, and are routinely using in the lab. Here you can see one of them real life inside a system, but I'll explain that a bit more later on. So I mentioned that we have to isolate these systems very well. So what we need to do is these trapping structures, before we can start trapping ions, we put them into a vacuum system. And this is a very good vacuum system. So the sort of vacuum levels we can achieve on the order of 10 to the minus 12 millibar. To give you an idea of what that is, if you were to step outside the space shuttle and took a big breath, deep breath in, then you would have a lot more air to breathe than in one of these things. There's nothing inside there. The reason is that when these atoms sit there, we don't want something flying along and bouncing into them. As soon as that happens, we basically lose information. So that's not very good. But we can routinely achieve these vacuums, but that's basically the sort of apparatus that we work with. Steel chambers with a few pumps on there. And then when we do things right, bingo, we've got our ions, where each one of these white dots that you can see here represents a quantum bit that we can now play with. Now it's a still image here, but these stay around. They can stay around for days. So they're very, very stable. Also, to give you like a dimension idea, so it's a 5 micrometer separation between the two. And please note that the reason they are 5 micrometers apart and they don't collapse into each other is because there's a Coulomb force. These atoms, or these ions, are positively charged. Two positive charges, they will repel each other, which means they can't collapse. That's really important because this Coulomb force we use to get these things to talk to each other later on. So there's a Coulomb force, kind of keeps them quite close. It pushes into these oscillating electric fields. They push them together, but the Coulomb force kind of pushes that out again. And that force gives us some coupled motion, which is important later on. Now, how do we encode information into these systems? So I've got these white dots sitting there in my trap now. Now I need to start doing some information processing. So first I'd like to encode some information. The way we do this in trapped ions is that we use the electronic state. So around this atom there's an electron flying around, and we can manipulate the way it's pointing or the way it's orbiting around the atom. And we can do this very well. So this this is basically new unit fidelity, how we can input the information in. So if the atom is then orbiting in a specific way, it's what we call the zero state, so that would be the analogous bit 0. And if it's orbiting in a different orientation, it would be a state 1. And to go between these two, we apply energy from the outside. This could be a laser, this could be a microwave field. Basically, you put in a specific amount of energy that allows you to change this electronic state from the one on the left to the one on the right. So we talk with these systems via some energy field that we apply from the outside. Now, if we want to do a gate, so for example, we'd like to do a controlled NOT gate, which means that depending on what quantum bit 1 is, we will flip quantum bit number 2, for example. These are important logic gates one has to do as part of algorithms. The way we do that is, what I mentioned before, is we use this coupled motion, so this Coulomb force between these quantum bits sitting in the trap, where if, let's say, the left atom is 1, it will push the right atom in a slightly different way. And that way they kind of feel each other, depending on which state they're in. So we transfer the information via this force that's kind of existing between the two. So if we want to do these things, we need to bring these ions close together. And that then, eventually, if you do things right, gets you a very, very small, in terms of computational power, quantum computer, which we have at Sussex. And we've got a couple of these setups now. Sure. Yeah.
Okay, thanks.
You okay?
Yeah.
Okay. Right, so now to give you an idea of where the field is, where's the quantum computing field with trapped ions. A lot of ticks here, some very impressive ticks. So we've entangled many ions successfully. We've also entangled ions with photons. So if a quantum computer is doing some operations and you like to communicate with another quantum computer in a different country, for example, one way of transferring this information may be via photons. So that is an important one. Teleportation, gate accuracy, etc. I've mentioned those. And we've also implemented some really nice quantum algorithms. And just to give you an idea of what people around the world really have been doing, some of them may look familiar to you, especially, remove the quantum bit, but the Fourier transform is part of many algorithms in classical machines. There's also a quantum Fourier transform, which is part of many larger quantum algorithms, and there's been a lot of great work at implementing them. So these machines are really running, and they're really doing some really cool stuff. They just need to be, scaled up right now. That's really the next point. So what is missing? We've done a lot of really great things with small number of ions, 2, 4, 10, 15, that sort of number. But what's really missing to give you some really amazing new results, a new drug or something optimized? And that's really scalability. And that's what most people are working on right now, and that's where a lot of the other architectures that I mentioned are struggling with. So there's some really cool systems which work on the small scale, but when you want to scale up and you want to have more of these quantum bits, just like in a classical computer where you want to have more bits and have more quantum bits, that's where a lot of them struggle, and where we hope that we have a good route forward. But a good question to ask is, well, how big do you need to go? How many qubits do you need? Earlier on, I mentioned that 100, or let's say 200 qubits already represent the number of particles in the universe, so why do I need so many? We should be done, right? But the problem is that even though we're maybe quite good in doing some of these operations with these quantum systems, we're not amazing, we're not perfect at doing that, which means there are errors. Just like in a classical computer, there are errors as well, they're just very, very low. Ours are a little higher, which means we need to perform some sort of error correction, which corrects the errors that we induce into the system when we operate with our quantum computer. Now, luckily, there are some very nice quantum error correction algorithms out there, and one of the most promising one is telling us that as long as all of your errors are below 1%, you're good. I can correct that for you. Now, the problem is that the way this algorithm gets around that is by using lots and lots and lots of quantum bits. So if you were at this 1% threshold, you'd need infinitely many quantum bits. So you want to be far, far away from that. You want to improve your error significantly, which is why that number, when I said 99.9, etc., that's why it's so important. The more nines there are, the less overhead qubits I will need to protect my information. And that's why a lot of the work that everyone does is just improving our way of interacting with these systems. But nevertheless, if we take the sort of numbers that we can achieve at the moment, we need millions of quantum bits. And this is normally where people say, okay, thank you, I go home. That will never happen anyway. Looks complicated enough as it is, but bear with me. We have a plan for this. So the first thing we need to do is we need to think of an architecture that can handle these sort of numbers of ions. So one thing we're going to start doing is to have these surface traps that I mentioned and then separate them out into different zones. And this might look familiar to you. All of a sudden we're going to have memory zones. So there could be memory zones up here. And then there will be processor zones where you process the information, then you park them again in the memory zone. Looks very similar to a classic computer in many ways. So that's kind of the idea, that what we'll have is different zones, and we just get the quantum bits when we need to do some processing in them, and then park them again in a memory zone. Ikke Trond from MIT has done a really nice representation of what this may look like. So this is running a quantum algorithm. You can kind of see these dots. It looks like a Pac-Man game. So these dots that fly around, they move between a memory zone and then go into an interaction zone, which will be somewhere. Then you can see these lasers that zap across. I don't know if you can see that. Can you obviously see that? So there's some, every now and again you can see some very short bursts of laser light. So this is this energy that we put in that then performs these quantum operations. And that's really what we need to do in real life. We're not that far from it. So I could, for example, show you this nice little clip here. So this is a trapped ion which has been moved around the corner, which is really the core principle of what we need to do. So not only can we have these ions which sit still and we can operate them, we can move these quantum bits around in space. And that's what you can see here. So this white dot is going from here, then up here, and back down. We can do this for a very long time. So that's been ticked off. We can do that. We can move these things around. We can move between memory zones and into interaction zones, etc. So that's not a major problem. One problem there is, though, is that these things that zap across, these laser fields that zap across, you can probably imagine that when I go really big, so when I have a million of these dots, and I need to carefully send these pulses of energy in the form of a laser beam without hitting any of the other quantum bits that are on this architecture, because I have to do these very precise operations on only very particular qubits here. This will get harder and harder the larger my system gets. At some point I'm going to accidentally hit a different ion. At some point it gets too complicated to control all of these individual laser beams. And that for many years has scared people a lot. Because there's, you need a million PhD students looking after a million laser systems and somehow hope that this will all come together on the same day. So that's a worry. There are ways around that, and people are doing some very interesting work to stick with lasers, but find ways around this. We chose to find a different way, and for us the solution is microwaves. Lots of reasons why we've done this, but I just highlight a couple. So lasers, some of you may have seen lasers, work with lasers. They're in your CD-ROM drive. They're quite good. But when you really want to use them to manipulate quantum information, then you have to work very hard to stabilize these systems and stabilize the amplitude, the phase, etc. It can be done, and people have done some amazing work with them. But we're worried when we're scaling up to the large numbers. Microwaves, however, are inherently stable. They're in your phone. We use them all the time. It's been extremely well developed. So it seems like a good technology to at least look at. Also, and I'll show you that in the last couple of years, we've come up with some nice ways of using this very stable technology to actually remove this very annoying scaling where, for every quantum bit that you have, you need a laser beam. And I try and explain that. So what we've done, so the first thing we did is we tried to use these microwave fields to do these quantum operations, these gate operations that I said are very important, especially the C-not operation, these controlled not operation that I mentioned early on. That everyone really has to do because it's a core principle of every algorithm. We've done this, and while there aren't that many nines here, it's 98.5%, just about on the fault-tolerant limit, this was our first shot at it. So, this was the first time anyone has done this particular gate, and because of the maturity of the technology, we immediately jumped to something pretty good in terms of fidelity. Most of the time when people start these sort of things, you start with 50, 60% and move your way up. We immediately jumped to 98.5. So, very happy about that, and we're very well en route to add a few nines to that. So that doesn't seem to be much of an issue. So microwaves, good, but we wanted to get rid of this annoying scaling, that every time we add a quantum bit, we need another field, microwave field or laser field, which really stopped us from scaling these systems up significantly. So we've come up with a, we think, neat way to remove that completely, where the end result is that you will need a handful of microwave fields, no matter how many ions there are in the system, how many quantum bits there are in the system. And that's quite substantial. I'll give you a very brief overview of how this works. So this is our surface trap again, this architecture where the atoms sit above, and you can see, these are the sort of memory zones, and I have to move around these areas. Now, what we're proposing is that if you zoom into one of these zones and you get into this gate zone, this processing zone, then inside this processing zone, we'd like to have a static magnetic field gradient. Now, the reason we want to have a, well, it doesn't really matter too much what this gradient does, but it helps us do some of these operations. But a cool side effect is that using this static magnetic field gradient, we can tune our qubits. And what I mean by that is that when I said we apply specific energies to these systems to do these gate operations, what we can do is we can change the required energy that we have to apply to do a gate operation. That's what I'm saying. So what we can then do is that depending on where in position along this magnetic field gradient I have, so basically here I have B field B1, and over here I have a stronger field. If I sit here, I would like to have a 12 gigahertz field coming in, and if I sit over here, I want to have a 13 gigahertz field coming in. Now, because microwaves are generally broad, you can't really focus these things, we basically radiate the entire architecture with microwaves, and by then placing our quantum bits in specific B field locations, we only make them resonant, we only make them feel specific globally applied fields. So this 12 gigahertz field will only talk to these quantum bits that are in a particular position in this B field gradient. And it doesn't see any of the other fields that I'm applying. So all of a sudden I can move all of these quantum bits into this B1 location, let's say, and it will interact with that one field, doing one particular type of quantum gate. If I want to do a different gate, I go to position B2, slightly different B field. It feels a different B field environment, and all of a sudden I need to apply different energy to change or to perform a quantum operation. So we'll only feel this separate other field I'm applying everywhere. And that's the crucial thing, that all of a sudden it's all depending on where I place my quantum bits that will determine what sort of quantum gate it does. Now, if I want to do a quantum algorithm, the important thing to note is that I will maybe want to do 5 or 10 different quantum operations. And I need roughly 1 or 2 fields per quantum operation, which means I only need maybe 10 or 20 fields, but it doesn't matter anymore how many quantum bits there are in the architecture. So, the important thing is we only need a handful of fields, no matter how many quantum bits there are in the architecture. That's really the take-home message. Don't worry too much about the details. And that really allowed us to start thinking about the engineering involved to build the big machine. Because before that we were extremely worried because we couldn't really make a good case in how to go to the million, hundreds of millions of ions. Whereas here we thought, okay, we cracked that bit, let's see what a big architecture would look like. So we teamed up with various people, including some people from Google to help us with the algorithm side to see how we can build this. Now let's start with the smallest unit cell of the quantum computer. That would be what we call an X junction, where our quantum bits basically move along this line here between different zones. This could be a memory zone, this could be a detection zone where I extract information, etc. So I've got a couple of zones here. A zone, for example, where I get my quantum bits. I need to load these ions like I showed earlier. Then there's this entanglement or gate zone on the left, and I also need to detect my information or store it. So that's my smallest unit cell. This stuff obviously needs to be fabricated. I mentioned this already, so I can skip over this. But just to show you, we've thought very hard about the sort of fabrication that would be required to make this architecture. And then we can go through the zones. So I mentioned that we need a magnetic field gradient. So we need to apply some currents to our architecture. So we developed a way to apply these currents to our architecture and only really affect the gate zone and nothing else. We also need to load and detect our quantum bits, and again, I mean, this is quite a lot of technical detail. If someone's interested, you can talk to me afterwards, but basically we have specific detectors in there which allow us to detect the quantum state, etc. And then we get to the electronics, and this is where it gets interesting. So our aim really is that we want to integrate all of the electronics required to operate the quantum computer into our chip structure. And I think that's quite important when we get to modularity, we'll talk about later on. So what we're really proposing is to have a microfabricated trap. So now the iron trap sits up here, and then we have different layers of different types of electronics. So this could be detectors, there will be some digital to analog converters, FPGAs, etc., all connected to the chip, until we get to a module. And that's then our quantum computer module, where the ions sit up here, and this is a reasonably large module now, where I think we have around 1,024 qubits on there. It's up to you how big you want to make this module, but we chose that particular number because we think that's quite feasible. And then you can see we've got the various electronics layers. Up here we've got some cooling as well to extract the heat that this machine will generate, etc. And I'll explain why we have piezos there in a minute. But one thing to point out, this might look maybe a little familiar. So I had a look at, if you get a picture up from what the current IBM microprocessor, for example, looks like, you've got layers of transistors and then various layers of routing all these electrical connections around. We have something very similar where we have a layer of a quantum bit, analogous to a transistor in a way, and a whole load of electronics layers behind it to control these systems. So it's not that different. It's quite different, but in terms of what's required from the qubit level downwards, it's actually not that different to what a lot of people are currently working on when they make these classical computer chips. Now, another important thing is, how do I go from many to many? So I really need to go from a module which maybe has 1,000 or 2,000 quantum bits to the millions. And that's really where we need to be. So somehow I need to connect these modules. Because at some point, you could say, well, why don't you make a massive module? At some point, Fabrication will say, wafer size, that's 5-inch, 10-inch, whatever you want to make. That's the maximum we can make. It's got to be modular. At some point, you've got to start again with a new system and then connect them some way. And there are various ways of doing this. One way is to use these photons that I mentioned. So what you could do is you could go to module A, let's say, and transfer the entanglement between an atom and a photon, and then send this photon along to the next module, and then you entangle the photon with the ion on module B, and all of a sudden you have these two modules connected. Is a way, and some people are working on that. We, again, seem to be different. We didn't like that too much, and I can explain why, but basically we use electric fields to connect these modules. And the reason we don't go for photons is because, one, it's very difficult on the engineering side, and also, if you look at the connection speed, so if you look at how fast can I entangle a photon with an atom or an ion, and then entangle that photon with another atom, that's quite slow. The world record at the moment, I think, is around 5 hertz. So while we don't care about clock speed too much, because these machines are amazing, that's pretty slow. So that's a worry. But people are working on increasing that quite significantly. But for us, using this electric field idea, which I'll show in a second, we're roughly 100,000 times faster without any additional development. And that's why we've come up with this approach. And basically what we're saying, which seems quite simple in a way, is just connect these modules close enough together so that we can physically transport our quantum bits between individual modules. And then the question is, well, how close do you have to get these two modules? How close does it have to be so that this ion that I showed you that moved around the corner, that will actually hop between two modules? And the answer is roughly 10 micrometers. That's small, but it's not that small. If you look at a lithography stepper machine, for example, these things can place things down to the nanometer scale. in terms of microfabrication, in terms of how well certain machines can place objects, that is not crazy. That is actually perfectly doable. But now you might see why we've drawn some piezos on there. If these machines aren't very good, if there are any imperfections, you can use these piezo actuators, which is basically material which changes size depending on what electrical signal are sent to it. I can maybe move these modules around to undo any errors. Now then we go bigger, so if you can connect these modules, that's not in the next few years, I can tell you that. This is down the line, where we'd like to be in 10, 15 years maybe. But that would really be a large-scale device where you have 2.2 million ions, which is really required and will be able to break RSA encoding and do some really amazing things. Now to kind of show you all of this in one movie, so unit cell, what we do is we load an ion, let's say, it pops up, really easy, and then let's say we move it across to the processing zone. In the processing zone, we'd like to do these quantum gate operations, so we apply our currents that give us our B-field environment that we need to have the selectivity, and we apply these global microwave fields which submerge the entire architecture. Then let's say they're entangled, and you've done some operations and you'd like to detect what quantum state it's in. Now, I didn't go into detail how to detect this quantum state, but basically we just apply one, and we only need one, laser field across, and depending on what photons we detect coming from this ion, we know which quantum state it was in. And then you zoom out, and this is basically just keeps on going. So here, for example, we're running a quantum algorithm to do the error correction, but you can run all sorts of algorithms on that. Then you get to your module size, and I've talked to you about what all these things are, but you see in a second why these piezo actuators are so important. So I place this on my steel frame, and I bring the second module in. And now I'm not as good as I thought I would be, and there's some misalignment. So what will happen is that the electric fields between the two modules won't overlap, and I can't transport my ions across. It won't work. So then I use my piezo actuators underneath each module to bring these things close enough together in the right way so that I can transport my ions across and thereby directly connected these modules. And now I'm in business. Now I can just scale up and put more and more modules together. Once that step is done, the rest is relatively simple. So from there it really scales quite nicely. And then obviously we get into the futuristic future. Wouldn't worry about that too much. Just we're on the connecting two module side, so not quite there yet. But this is most certainly the vision forward, and I think the important thing is to know that we can do that, because otherwise, why work towards that anyway? We're quite happy that we have a way forward and we know what the big machine roughly will look like. Obviously, not as impression in many ways, but we're quite confident that the trapped ion approach and our specific approach that we've developed has a very clear route forward, and we're working very hard along these lines at the moment. So what do we know? I think the first one is quite important. Up to maybe a couple of years ago, and maybe even until we published this blueprint, people thought you can't build this. You can maybe build a 100 qubit machine, or maybe 1,000 if you're good, but you're not going to get up to the numbers that we all know you need. We feel this has really been changed a bit now, and we're very confident that these machines can be built. It's just a matter of time, engineering, and as always, money. In terms of timescales, so we're currently working on the demonstrator device. Now what the demonstrator device is, it aims to demonstrate every core principle of the module that I showed you and connect two modules. Everything in one system. So far we've demonstrated a lot of these things in separate systems. We need to bring everything together, and that's what we're doing right now, and we're quite far along, but I think fair to say it's roughly 2 years until we get to that point where we can show that full system running. And then when we talk about this large-scale quantum computer, and I haven't really introduced this universal word yet, but we can always say we have a quantum computer because it can do certain things, certain quantum things very well. A universal quantum computer, you could run any quantum algorithm on and it will just work. And to get to a universal quantum computer, which isn't a purpose-built machine, it can just run anything, we need these millions of qubits. And this is really the holy grail, so to speak, of quantum computing that we're all working towards. Well, and the last point is hopefully true, that we most certainly are very hopeful, and we strongly believe that these machines, while they may take a little bit of time until they come about, will transform science and society completely, but we don't even have a clue yet what exactly these machines will really be capable of doing. And I think that's a very exciting thing to think about. So I'm going to leave you with the question, what could like an incredibly, unbelievably fast machine which uses a completely different technology do? That's a good question to ask. We ask these questions all the time to industry, etc., for people to think about what this technology can do. And it really needs a lot of people to think about this. We won't have all the answers. It's almost like a community thing, really. And that's where I finish. Thank you. Questions? Yes?
Will your demonstrator be able to implement a Turing machine?
Implement a...
Turing machine?
No. I think, no. So...
Will the one in 10 years' time be able to?
Hopefully. Don't know. Hopefully. I'm very hopeful, but I'm always careful with timescales, so to speak.
So in what sense is it a computer if it can't implement a Turing machine?
Well, I think at the moment the reason why I'm hesitating is that we just need time. If you look at the sizes that we have, they're not very powerful just yet. We really need a lot more time. We need to get the number of qubits up so that we can actually get to a state that we can start looking into these sort of things, which is not ready yet. Oh, any of you?
Quantum tunneling, is this a problem, or are you able to contain your...
Not a problem for us, no. So those effects were not that small, so that doesn't come in for us, no.
Okay.
It's a cool effect, but actually we don't have to worry about that. Yeah.
I'm afraid you lost me early on when you used the expression a couple of times, all at the same time.
Yeah.
So how can something be on and off all at the same time?
Uh-huh. Yeah. Right. Yeah. Well, that's the. So I mean, one thing to note is obviously when we look at it, it's not anymore. So that's this weird thing. As soon as you interact with the quantum system, you look at it, it collapses into either 0 or 1. But what quantum mechanics says that on the very small scale, when you don't interact with it, when it doesn't interact with the environment, it can be in any of these possible states simultaneously. But as soon as we interact with them, as soon as we look at these quantum systems, they collapse and become classical. And this is why we don't really observe any quantum effects in our world, because when we interact with each other, our surrounding, it becomes inherently classical. But it's just the weird feature of quantum theory that when you have the right sort of system, well isolated, ready to observe these quantum effects, that it can be in this superposition. Yeah, absolutely. Yeah. I don't know who put their hand up first. Any of you? Go for it.
So you showed that with the microwave signal to interact with to learn how close can you basically put those frequencies together, because you have tolerances in manufacturing depending on where you put it. So what is your spacing?
Yes, that's a good question. So one, we don't have tolerances in fabrication. That's really important. For us, we have full control over where we place these ions, which means it's down to the precision of the voltage signal almost that we send in, and this voltage signal produces an electric field which pushes the ion into a specific place. So it depends on how precise we can do that, but we can do that down to the nanometer scale. And then it depends on how strong your B-field gradient is. That tells you how careful you have to be in placing that. But to be honest, the sort of bandwidth that we have is many megahertz, and SIG nodes, tens if not hundreds of megahertz, and SIG nodes can be as close as, depending on how strong these SIG nodes are, 100 kilohertz or something. So we can most certainly fit in the 20-30 fields that we know that we need into our bandwidth. A very good question. Yeah.
So you mentioned that there are different ways of writing algorithms for quantum bits compared to normal computers. Does that mean that after these things, suppose they become widespread and everyone has their own quantum computer, does that mean that our body of knowledge of computer science, as we have it today, would it go obsolete?
No, I mean, okay, so a couple of things. One, I think so you're absolutely right, these quantum algorithms, they're different to classical algorithms, and it's very difficult to write them purely because there's almost a lack of knowledge there, and there's a new wave of skills that come out of this where people will get trained in developing quantum algorithms, and they may become quantum computer scientists, I don't know. But the quantum algorithm development is a big thing, an up-and-coming thing, and the sort of backgrounds that people at the moment have, you need a bit of physics, maths, but the computer science side is still really important. And especially right now, where actually most of the work that we do is try to understand a classical algorithm, understand where the bottleneck in computation is, and then see if there's a quantum algorithm or a quantum algorithm we can develop that kind of opens that bottleneck up a little bit. So for a very long time, long time in the future, I think we need both, because otherwise this won't work. So don't worry, I don't know if you're a computer scientist, it's not going to be obsolete anytime soon.
A question related to his that's probably the answer as well. In which kind of algorithms are quantum computers worse than normal ones?
Sorry, can you say that again?
What kind of algorithms are there for which quantum computers are not as good as normal computers?
Well, I think all of the quantum algorithms, maybe someone has developed one and then binned it because it wasn't as good as a classical algorithm. So I think all the ones that have been developed, they're equally as good-ish or better. I think there's a question of resources. If something is almost as good as a classical computer, you wouldn't want to trouble a machine like that for that at all. I don't, and maybe that will be a quote later on again in 100 years' time, but I don't envision these things doing any the sort of normal tasks that we do on a day-to-day basis, when you write a document or these sort of things. I think what we can envision, certainly in the next 10, 20 years, is this code processor idea, where you might have a big quantum computer, and I should have said, these things are big. The final picture that I showed you, I think the Daily Mail, I'm not that proud of it, but the Daily Mail covered this story and said, oh my god, football pitch size quantum computer. It is that big. So the final picture that I showed you is roughly football pitch size. Sounds scary, but shouldn't. If you look at some of these big data centers, they're even bigger than that. But also the important thing is that the better we get interacting with these systems, the better we get in doing these quantum operations, the smaller these systems get. And we're most certainly, these numbers that I put there and these sizes that we have is using currently available technology. And that's the big thing, that the statement we've made is that using today's technology we can build this machine. There's nothing new we have to invent, so to speak. There's no roadblocks apart from money, engineering, etc. This can be done using today's technology. So, trying to come back to your question exactly.
So basically, what you're telling us is you wouldn't use a football-sized computer to do word processing.
No. So I think what would happen, maybe I'm wrong, but I think what we feel at the moment is that this machine would sit in the desert somewhere doing its thing, and you will run a very data-intensive operation. Some big data thing, something you want to do which is really complicated. The classical machine will do everything, all the front end and the back end stuff, but somewhere in the middle there will be something which the classical machine just doesn't like. It's really difficult at solving that particular problem. That you will outsource via the cloud to a quantum computer. It will solve that for you, send the answer back, and the classical machine will keep on going. Because the money and the resources involved in running these machines, it's not going to be cheap. Which means you want to be careful about the sort of things that you run, at least at the beginning. And I think it makes a lot of sense to still have the classical machines do the things they're naturally good at, but the stuff they're really struggling with, that you would outsource. So I think both types of machines will work together. Yeah.
I didn't get how entanglement is used in your computations.
Yeah.
Could you give some insight?
Sure. The way you could imagine is the superposition gives you all these different possibilities, but somehow you need to connect this entire quantum computer so every qubit knows what the other qubit superposition is doing. So what the entanglement is doing is basically connecting all of these quantum bits together, so it becomes like it's one big state, one big system. It wouldn't be if it only had the superposition bit. you could officially simulate that thing on a classical computer. It wouldn't be anything super amazing. But with the entanglement included, it kind of connects everything up in a way that is required. So it's really just to connect up all the particles.
So do you have to quantum entangle all of the qubits at the same time, or does it change between?
Well, not necessarily at the same time. You can do this one after the other. You just have to do this fast enough. You don't want the first entangleness to disappear because of errors, etc., by the time you get to the other side. And this is where error correction comes in. You kind of build up this error-corrected state, so to speak, and then you can go bigger and bigger. And once you reach the sort of fault-tolerant threshold, you could, in theory, keep this quantum state alive forever. And then you could grow this. You don't have to do this at the same time. But you have to make sure that every bit of entanglement that you create, that even the small system, that you keep this alive, because these systems are very sensitive. Any interaction with the environment and these systems just collapse and you lose all of the information in a way. But you don't have to do this at the same time.
Is it then comparable with an FPGA where you have your where you have an application which you implement on your quantum chip and run that application, and then very fast? And then if you want to change it, if you want to analyze something else, like if you do an FFT or so, you do it on that one. If you want to do another operation, you change your connections and entanglement, or is it right?
Yeah, in a way. I guess you could think of it that way. Yeah. I think you've had your hand up.
I was interested in the vacuum technology that
Yeah.
you use. Your vacuums must be very high.
Yeah.
And you're not going to be using a traditional pumping system that just sucks the air out.
Yeah, so we start with a turbo pump. That gets us down to roughly -6. Then we put it in an oven, bake it 200 degrees C for roughly 2 weeks. Then we turn on an ion pump. And after that, we turn on a sublimation pump. That then gets us down to -12. But once that system, once that's complete, there's only an ion pump running.
Okay.
So once it comes out of the oven and it gets on the experiment,
That's sufficient for the leaks and the secret.
yes, there's only one pump, the ion pump, and that
Yeah.
runs forever. I mean, we've had systems sitting there for 5-6 years. You don't have to touch them. Well, let me go around.
Including your fabrication costs, what's your electricity bill?
Luckily, I don't know. The university kind of pays for that. I don't know. However, one thing we did do, and I can get the number out of you. We actually looked very carefully at the power dissipation of this system, because we're really worried about that, and we still are worried about that because of all the electronics we put at the back. We've got these large currents that we apply. The power management is really important, and as part of this blueprint work, we looked at that quite carefully. What I can say, and I just don't remember the exact number, the end result is that the power density, so to speak, per qubit centimeter does not exceed modern CPUs. So we're not beyond that. But imagine then your modern CPU football pitch size. It kind of gives you an idea of the consumption. So it's a lot now. It'd be a lot more before. And I think some of the calculations hinted that if we had the big thing, you need a big power plant near it. Should be fine.
Vacuum doesn't conductate a lot either.
Yeah, absolutely. Yeah, there's which to some extent is good, because I didn't go into detail, but we'd actually like to operate at roughly 80 Kelvin, because the chips that we use, silicon technology, is useful to use, gets very conductive at 80K, and helps us with the heat management. So if it was very conductive, we wouldn't be able to get down to 80K. So it kind of helps, but it's also a pain. Yeah.
Whenever I see people talk about these quantum computers using ions, they always use the term ions. Is there research in what kind of ions are used and advantages to?
Yeah. It's almost I don't want to say personal preference. I mean, so we use ytterbium 171. There are people use all sorts. There are people use calcium, beryllium, barium. Lots of different systems. You'd like to have some sort of spin half system that helps, that limits you. You'd like to have something stable, nothing radioactive or something that decays too quickly. So that limits you a little bit. But some people prefer lighter ions, like the berylliums, the calciums. We prefer a heavy one. Ytterbium is very heavy. Whoever you will ask, they'll have their personal preference for why they want a particular type of ion. So it's open. But right now, to be honest, people have done similarly amazing things with different types of ions. So there's no strong, it's not like it's got to be a terbium, it's got to be calcium. That's not clear at all.
What justifies your preference for it?
So for us, I could tell you, we like a terbium because so we still have to use some lasers, just not for the quantum information processing. So for the trapping, for the cooling, we need to cool our quantum system, only these quantum bits, we use lasers for that. They're all in very nice wavelength regions. We start at 369 nanometers, which is a bit uncomfortable, but okay, and then go up. All of these systems are commercially available. Fibers work at that sort of wavelength, which is really important for us. And it's nice to prepare and detect the quantum states. There's a lot of technical type of reasons, but one of the big ones is the availability of the technology required to build these things. And same for the microwave frequency that we have to apply is 12 gigahertz, 12.6 gigahertz. People seem to like that frequency in industry. It seems to be an okay frequency to work with. And there will be others which they will be at 8 gigahertz or 20 gigahertz, etc.
How much do you think a viable quantum computer costs?
I knew that question was going to come. We made the mistake, well, I don't want to say mistake, but we just one day say it would be 100 million. It'll be a lot more. It will be, if we're talking the big device, hundreds and hundreds of million, no doubt. But again, it doesn't worry me that much because if I think about how much we invested at CERN, for example, and some of these other big facilities, billions, and that's most certainly the level that would get you to, we would hope that would get you to that sort of level. And remember, this sort of machine would be able to, for example, do this sort of Higgs boson research, etc. So these machines could simulate a lot of the stuff that CERN currently is doing. Not saying CERN is bad or anything, but it warrants also investing into these sort of machines because they can do a lot of these things that the research facilities are currently already doing.
I was wondering if there was a comparison to be made with massively parallel computing, which seems to work on similar algorithms.
Yeah, so I think I always like to think of this as like a massive, almost infinitely large parallel classical computer. One can think of it that way, but it just doesn't encapture everything. It's a nice way of thinking about it, and especially when you think about the sort of applications this device will have, because it just does a lot of things in parallel, but it just doesn't capture everything. It's not identical to a classical machine which has lots of cores and you just do lots of things at parallel.
And they have similar problems in finding people to program them and so on, and
right.
a smaller class of problems that can actually be solved on them, etc.
Yeah, so in that way, absolutely. That's most certainly the state we're in at the moment.
So when we've got one of these machines that can model every particle in the universe, can we predict the future with it?
No comment, I don't know. No idea, wouldn't it be great? I don't know. But these sort of questions, because we literally don't know, because it's such a groundbreakingly new and different technology, the possibilities are potentially limitless. Really, it's down to us to actually come up with what we can use this new technology for. It's not that the technology itself is limited in some particular way right now.
Yes, sort of solving chaotic systems and things might be within the realm.
Absolutely, yeah. Yes, that's right.
So how many qubits would your demonstrator contain?
Good question. PhD students are going to hate me if they see me say this. I think we would like to get to this sort of anything between 20 and 50. I'd be very happy with, especially getting closer to the 50 would be great. But I think even on the sort of around about the 20 side is already good. One always has to be careful when you give a number. I can go right now. I can go into a laboratory, go to one of these systems, and I can trap you 100 ions. Would take me not long at all, maybe an hour or so. Really easy. But being able to individually control them sufficiently that you can do something useful with them is a completely different game. And that's really the difficult bit. It's not to hold these ions in these pictures that I showed you, that's all great, but to do these precise processes that we need to do within these gate operations, that's the challenge. And that's where we have to see how far we can push this within 2 years. But this is most certainly, I haven't mentioned this, but we're most certainly keen to turn this into a spin-out at the 2-year mark. So this will be turned to a company to then get the required investment, etc. So we need to see how far we can push that before then.
So when qubits move around the components of the quantum computer,
do
they have a particle behavior or the wave behavior?
Particle. That's a particle that we see as particle, yeah. You can model it as a it's a particle.
I don't know whether this is a sensible question or not, but
Sure.
your quantum algorithms presumably get their speed because of the superposition of states, so they're essentially doing all possible things at the same time.
Mm.
But you say when you observe them, it collapses into the classical state.
Yeah.
How do you know that the classical state is the right answer?
Yeah.
Which one does it collapse into?
Yeah, so there are two things to address this. So the first thing is the way you... So you can obviously see there's a problem, right? I can use 200 qubits or maybe 1 million in the end to represent the number of particles in the universe. But really when I start looking at it, they all collapse into, well, let's say 2 million bits, which is a bit annoying. So what these algorithms need to do is they need to do all the processing. There's massive amounts of processing, why we kind of don't look at it, so why we do these operations before we detect. And then we need to, well, we say interfere, these are all wave functions in the end, but we need to basically bring the system to a solution that it kind of collapses onto its answer, so that when we then detect, the answer will be maybe a 2-bit number, so it might be, well, whatever the answer then is. But you don't get all of the information out. If you then want a different subset of information, you will have to change the algorithm so that the system in a way collapses onto that bit of information that you want to get out in the end. And this is why the algorithm development is different to what you do for a classical computer. So that's number one. The second one is the verification aspect. And that's a big topic. Because how in the end can we verify that what we've done is correct if nothing else can simulate it or get us anywhere near understanding what these machines are doing? And that in itself is a big part of research and coming up with techniques to verify these machines. So that's an area that people are working on, and we need to do a lot more on. Absolutely. But I've had a lovely discussion earlier on the machine learning side as well, and on explainable machine learning. And with machine learning, it's very difficult to know what these machines are doing when you get an answer. And people are working on trying to understand the reason why the machine gave you the answer. It's similar here. We need to understand what these machines in the end did and why they gave us the answer that they gave us.
Hi, you mentioned the wave particle duality there, because you're a physicist and you're here. Can I ask you the alternative view is the quantum field theory view? So there isn't a particle; it's just fields.
I'm not a field theory expert or anywhere near.
I know the sort of two competing theories, and I was raised on wave particle duality. Quantum field theory came up, and it sort of connects the forces together in the gravity waves and that sort of thing. That doesn't impact at all on your...
No, and I wouldn't be able to give you a satisfying answer, I don't think. Sorry.
You mentioned manipulating these ions using external sources like lasers.
Yeah.
So does the wavelength of the laser and the size of the ion need to be certain?
Yeah, so the energy we impart on the system depends on the ion that we use on, in terms of our new approach, exactly where in the B field it sits. That will basically tell us what sort of energy we have to put in. This could be a microwave field, this could be a laser. So yeah, for whatever we want to do with these atoms, you need a specific type of laser or microwave source, whatever the energy is that you apply from the outside.
You're operating essentially at the atom level. So is it, I know it's not a right way to think of it, but when we think of a bit on an electronic wafer, it has a certain physical size. I assume a lot more than one atom. And then we have just one atom representing a qubit. So you're also reducing the size, physical storage.
The size of a quantum computer was like a classical.
Yeah, I mean the amount of space or physical matter you need to store data.
Well, I think if you look at the underlying architecture that confines like one quantum bit, for example, it's bigger than an atom that is required to actually hold one bit of quantum information. I wouldn't say we're making it smaller than a classical by any means. I mean, the interesting thing is one of the reasons Moore's law is really, breaking down is because they're making these transistors smaller and smaller, and they're getting into the quantum regime. They're being actually, really hurt by some of the quantum effects that happen because they're making their transistors smaller and smaller. And at some point, you get to the single atom transistor, basically. So they're hitting it from the other side, whereas we already sit comfortably within that regime that they're hitting.
How many quantum computers are we going to need? The guy in the 50s said we need 10 computers. How many do we want?
Is that still running? I don't know. I'd be so happy with one for now. However, having said that, I think when these machines are really ready and you can do some really amazing things for them, people will want to use them. And when I say, we always say some of these things that take 1 billion years, this would take a second. Really, these things take some time. They need some time to operate them and set them up, etc. So I think if demand is large enough, and it should be, given the impact we expect from these machines, you need a lot to cover the demand. So I think if they do what we hope they will be able to do, 5 ain't going to do it. There will need to be a lot more.
Once you make one quantum computer, a bit like a Model T, you can make lots of them very cheaply?
You can make lots of them.
Once you make one,
yeah,
then you can make infinite number.
Yeah, absolutely. I mean, once we know how to do one, I think it would be a lot easier to make more of them. The cool thing is, if you think about it, couldn't you then use a quantum computer to optimize the next quantum computer?
Exactly.
Because it should have the... Sorry?
It might be the wrong sort of algorithm.
Might be, yeah. But basically, this is something to think about, and we're already getting into this point right now where, especially on the machine learning side, and I didn't have time to talk about that, but there's a lot of cool stuff happening in machine learning, where machine learning can help us, and we can help machine learning quite a lot. And this we're getting into that regime where there's like a give and take, almost.
If you have a universal quantum computer,
yeah,
you can then emulate any other potential quantum computer.
Yeah.
As Turing would have said.
Would be the hope.
Yeah.
We could be inside one.
Yeah, but
how do you start this system? As in, how do you get your specific ions in specific locations? Are you using different microwave frequencies to individually locate the particles at the beginning of the system? Or how do things get going?
How do they get going? Good question. So if we go back to, where are we? Our unit cell here. So technically, and this won't be part of every extraction, but you load an atom, and there's a process involved in doing that. But let's say I can place an ion on this surface structure here. I would then have to apply some electric fields that kind of push the ion along wherever I want to go. So let's say I want to go to the processor zone. In the processor zone, I then need to initialize my system. So I need to basically input the information that I'd then like to have processed. And so this could be, the 0 or the 1 or some superposition between them. So I initialize that, and I do that using lasers or microwave fields that basically operate this qubit, that change it from the 0 to the 1 or something in between. And then you run the algorithm and do lots of operations on them. That all happens in this entanglement zone. So then you move this to slightly different places, so it fields different global fields. And once the algorithm is done, you may then want to move it into a detection zone. You fire a laser, and then we only get 0 or 1 out. And that's then how we get some of the information out of the system. Yeah.
Can you tell us a bit more about quantum machine learning?
Yes, I can do that. If people are happy to stick around, absolutely. Because I'm half prepared. Right. So, quantum machine learning. 2 slides, very quick slides. So, machine learning, hot topic at the moment. Very cool field. We've done quite a bit of work on this, and other people as well, not just us, to see what quantum machine learning can do. And there are already some quantum machine learning algorithms out there which look at, for example, binary classification and also k-means clustering, really where you look at large data sets and you'd like to find either some sort of pattern or groups within the data that you might be interested in. So you can use it to understand your markets better. Facebook might use it to understand the customers, or not customers, I shouldn't say that, I guess, their users, etc. Now, when you then think about what machine learning does, and I'm not a super machine learning expert, you can correct me if I'm wrong, but when I think about machine learning, it's really manipulating really large vectors in really large vector spaces. That's really what you do in machine learning. Quantum computers are the same thing. Really, quantum computers the state can be represented as a vector, and we then manipulate this vector in a specific way. And to give you an example, so I can write my 0, so the quantum bit 0 or quantum bit 1 as that vector up there. So 1 or 0, it's that matrix. I can do that. Now, the qubit can be a superposition between these two. So one qubit lies in this complex vector space, two-dimensional complex vector space. Now, if I put multiple qubits together, so I have multiple 1s and 0s, and I put them together, let's say I have n qubits, then what I find is that all of a sudden I live in a 2 to the n complex vector space, where n qubits live in a 2 to the n dimensional vector space. Now, if you then think about what does that really mean, if I have some classical data, a list that you might want to have, and you represent that in this way, which you can do. It's literally just a list of data that you have. Then you will need to represent a 2 to the n dimensional vector. You will need 2 to the n bits, or just n qubits. So in the quantum way, the way you would write this is like I've written this, down here, where you have your quantum data, which could be this sort of list, which has 2 to the n components for n qubits. And this is, it's difficult to do this in such a short amount of time, but the core principle is really the superposition here and connecting them together in such a way that for n quantum bits, it can be represented, or it can give you 2 to the n dimensions. That's really the really important bit. So you can represent a huge amount of data, a massive amount of vectors. Just imagine one vector can represent a very large amount of data. A quantum computer can do that with n bits, whereas you need 2 to the n classical bits to represent the same system. And because quantum computers just naturally move these vectors about, it's a very natural fit, and this is why quantum machine learning is such a hot topic at the moment. Don't know if that answers your question, but so does that vaguely answer your question a little bit? If you're interested in that, we can talk about this afterwards as well. But this is most certainly a hot topic, purely because the underlying principles are so similar. Machine learning and quantum mechanics, or how these quantum machines work, they share a lot of similarities. So it's natural to look at these things, and my hope really is that whatever these great machine learning people do, we can kind of jump on the bandwagon and be like, well, great, thank you for finding this amazing application. We can probably do something similar, but better. See if that works out. Thank you.
I think we've probably got time for one more quick question. And then
I have no more slides, so...
I have a question.
Yeah.
Is anybody thinking of doing stored program quantum computers that can execute?
Doing what?
Stored program quantum computers.
Stored program.
Von Neumann machines.
Yeah.
Where the program is stored in qubits.
Where the program is stored in qubits. Not thought about that.
Because it could execute a lot of programs.
I'd have to think about that. Pass. Z9. Okay. Great.
I'm afraid we've run out of time. I get the feeling that we could probably stay here all night. But thank you very much for